P.K. Tulsi, respected Maitri Datta, dignitaries at different nodal centers, local coordinators, and my dear participants. A very good morning to all of you. First of all, we are really very sorry for this interruption due to power failure at our end. And so that is why there was some delay in this inaugural session. Myself, Rajesh Mehra, I am coordinator of this program, and on behalf of this coordinator of this program, I welcome all the participants in this program. Actually, this program is based on VLSI design, and we are going to run it for one complete week. This is the third program we are conducting in this area. Earlier we conducted a similar program last year. Two programs were there. One was in the month of March, another was in the month of November. And in those two programs also we got very good response from all over India. In our first VLSI program, we got 20 nodal centers, and in the second one, we got around 14 nodal centers. And in this program, we got requests from more than 30 nodal centers, and we sent confirmation to 28 nodal centers. And at present, we are going ahead with these number of nodal centers. We are really thankful for this overwhelming response in this VLSI design program. Actually, in this program, we are going to include theory as well as practical aspects. To cover these aspects, we have invited speakers from IITs, NITs, and different industries. And during this one complete week program, first of all, we are going to start with CMOS overview, then analog CMOS design, then advanced MOSFET, and these topics will be touched by our expert from SCL Mohali. Then it will be followed by high-speed interconnects. Expert talk is arranged on this topic by our expert from IIT Ropar. Then we have 3D device simulation modeling. That is basically virtual fabrication of transistors, and you will get exposure of virtual fabrication of transistors and their simulation, and that part will be done by one engineer from Cadre Design Systems, New Delhi. On third day of this program, we have one more this topic, that is your low power VLSI design and Verilog based VLSI design, and this topic will be covered by our expert from NIT Kurukshetra. In the after lunch session, we have analog design simulation part, and that will be done by engineer Deep Sehgal from SCL Mohali. It will be followed by digital design simulation, and that part will be done by one engineer from NTUPER Technologies from New Delhi. Then we have expert from NIT Hamirpur, and that expert is going to give us exposure about high performance CMOS design and VLSI interconnect designs. And at the end of this program, expert from IIT Roorkee is going to come, and he is going to give us the idea about novel multi-stage transistors and nanoscale VLSI design. So this is a brief overview of this complete STC program, and this time schedule is already circulated to all the nodal centers. And now after this one, I will give brief. Basically, I am going to introduce the name of different nodal centers connected during this program, and these nodal centers are ABS Ghaziabad, JSS Noida, MMM University of Technology Gorakhpur, Uttar Pradesh, Rewari Institute of Technology Rewari, Haryana, NSIT Patna, RKGIT Ghaziabad, Aryabhat College of Engineering Ajmer, JECRC Jaipur, HITM Agra, WCTM Gurgaon, Khalsa College of Engineering and Technology Amritsar, DIT University Dehradun, Institute of Engineering and Technology, and then Banastali Vidya Peeth, University, Rajasthan, JCDM College of Engineering, Sirsa, Haryana, NC College of Engineering, Panipat, Gyan Jyoti College of Institutions, ICL IIT, Ambala, AIT Tonk, Rajasthan, Mewat Engineering College, Haryana, MIT Muradabad, Universal Polytechnic College, Laluru, GTBIT Delhi, Thapar Polytechnic College, IGDTU Delhi, RD Engineering College, Ghaziabad. These are the list of centers, and most of them are connected with us. And our team is also in process to connect all other remaining centers. And now it is time to invite our HOD of Electronics and Communication Department, Dr. Maitri Datta, to give her views for this program. Dr. Maitri Datta, please.
Very good morning. First of all, I just welcome Dr. P.K. Tulsi, who is the Dean Research and Development of NITTTRCHD, and she is Professor and Head of EMGT Department. Thank you, ma'am, for coming here for the inauguration of this course on VLSI design. And I also congratulate Dr. Rajesh Mehra, who is the coordinator of VLSI design, that on his, on your request and on his hardworking effort, we could connect so many centers today for this ICT course. And I thank all the centers who are connected with us with your participation, and I expect that 100% participation from your side will be there for this 5 days week. And I just request that the coordinators of various centers that you just take consideration of our request, that you request all the participants to sit for the full time for this 5 days courses. Otherwise, you know that of these ICT based courses, finally after 5 days we see that some participants are attending one session, some participants are attending the next session, and finally, though we are giving the certificates, but the final and the complete knowledge of the subject are not coming up with the students, participants. So this is my humble request to all the coordinators, that they should take check with all the participants, that they should take the participation for the full 5 days. And I also welcome all the experts and who are the guests in different institutions who have come here to just inaugurate or to address the participants. And definitely Dr. Rajesh again will take up this point, that to introduce the guests from the other centers, other remote centers. And for of this course, I just want to say that as Rajesh has already conveyed to you, we have called many experts from IITs, NITs, and the industry people also. And I expect that all those experts will give their 100%, and you also will receive 100% knowledge of that topic. And I just convey my expectation that you will get more knowledge about this topic, VLSI design. At our department in Electronics and Communication Engineering department, we have 5 laboratories in DSP and soft computing laboratory, then computer network laboratory, then communication laboratory, then embedded system design laboratory, and also a very strong laboratory on VLSI design. Recently, we had purchased a VLSI software, as I have seen in your timetable also. One person from Cadence industry, he is coming here for demo of some VLSI software. So we have purchased the proprietary software on VLSI design, which is dependent on the Linux operating system, and we are going to set up a very good established VLSI system design laboratory in our department. and basically there are so many centers, so the introduction of all these centers will not be possible. So I just request Dr. Rajesh that you can just ask that those centers who have called the experts from outside as a guest, so that they can give their own view for this our courses, which can be suggestions for our own course, how to improve, or how to in further courses we can improve this type of courses. So I just want to get some comments from the outside experts. And thank you so much, and I just give my best wishes to all the centers, all the participants, all the coordinators, and also to Dr. Rajesh Mehra. Thank you.
Thank you very much, ma'am, for your best wishes. Now I invite chief guests at different nodal centers. So please, I request our local coordinators at different nodal centers to kindly introduce their chief guests at different nodal centers. So if you have called external chief guests at your nodal center, please go ahead with the introduction, please. Yes. ABS Ghaziabad. Or I think we can go ahead with the brief introduction within 1 to 2 minutes. You can introduce your center, and you can also give us information about the tentative number of registered participants. So please be brief in your introduction. First of all, I invite ABS Ghaziabad. Okay, JSS Noida. ABS Ghaziabad, your mic is off. Kindly switch on your mic, please.
Sir, good morning.
Good morning.
ABS, sir, good morning.
Yeah, please go ahead.
Post coordinator, Dr. Rajesh Mehra sir, and all the speakers, all the center coordinators and participants. I, Dr. Rajesh Kumar, head EC department, take this opportunity to welcome all the dignitaries present here, dignitaries and participants present here at our nodal center. So, we are total here about 47 participants registered for this center. And I'm expecting that the next 5 days will be very good learning for all of us. And thank you very much, sir.
Thank you very much. Now I invite JSS Noida. JSS Noida, can you hear us? So we can move to the next one, M University of Technology, Gorakhpur.
Hello. Good morning, Dr. Mehra.
Please be loud. Actually, your voice is not clear.
Hello.
Yeah, please go ahead.
Yeah, my voice is clear.
Yeah, now it is
Okay.
fine.
Good morning, Dr. Mehra, and good morning, Madam
Good morning.
Tulsi. We have heard Madam Tulsi also previously in our institute, and this is our second ICT based course. We have total 40 registered candidates, and the institute has invited 2 more institutes which is near to this our institutes, and from there 2 candidates have come. They are also registered for this course, and we have a participation from computer science department of our institute, electrical engineering department from our institute, and myself from electronics and communication engineering. So this is all about our Madan Mohan Malviya Center.
Thank you. Thank you very much.
Okay, thank you.
Next is Rewari Institute of Technology, Rewari, Haryana. RIT Rewari. Then we can move to the local coordinator from Rewari Institute of Technology. Who is the local coordinator? Dr. Dharmender Singh. Okay, then we can move to the next one. NSIT Patna. RKGIT Ghaziabad. RKGIT, can you hear us? Then Aryabhat College of Engineering, Ajmer. Good morning.
I'm Ashish Golani from Aryabhat College of Engineering and Research Center.
Okay.
We have 54 participants which participate in this conference or training program. Thank you.
Okay, thank you. Next is JEC RC Jaipur.
Hello sir, good morning.
Good morning.
I'm Upesh Kumar, the coordinator for this workshop here in JCRC. We have inaugurated our workshop at around 9:30 a.m. in the morning. And the chief guest was Mr. Dr. P.K. Chandna, our principal, and expected participants is about 50. And we have just reported around 40 candidates till now, and some more yet to come.
Thank you. Actually, I just want to share one important information with all the nodal centers that in this program only faculty and staff is allowed, and we will be able to give certificates to only faculty and staff. This course is not meant for students. They can join this program, but they means certificate can't be given to the students. So whatever number you are giving us here, and that number should be from your faculty or staff only, right? Next is HITM Agra.
Good morning. Good.
HITM Agra.
Yes, good morning, sir.
Good morning.
I S.K. Trivedi, head of the department TC.
Your voice is not clear. Please be loud.
Hello.
Yes.
Good morning, sir.
Good morning.
I S.K. Trivedi, head of the department electronics and communication engineering. Thank you for selecting ICT based VLSI short-term program by you. As you know, HITM is the first nodal center from the UP, and we are thankful to you organizing such a wonderful short-term course, and VLSI is very useful for the faculty, staff perspective, and also for students. And there are 35 participants in our center from the electronics, electrical and electronics, computer science, faculties and staff from our college and also from other institutions. Thank you.
Thank you very much, Professor Saab. Now I invite WCTM Gurgaon. Okay, there is some problem with this center. Next is Khalsa College of Engineering and Technology, Amritsar. Khalsa College of Engineering and Technology, Amritsar, Professor Sanjeev Kumar.
Hello.
Yes, go ahead.
Hello, good morning, dear sir.
Good morning, please go ahead.
Can you hear me?
Yeah. You are.
Hello, I am Sanjeev Kumar, Head of Electronics and Communication Engineering Department. We have 34 participants in this program, which includes faculty of ECE and CSE department. Thank you very much, sir.
Thanks a lot. Next is DIT University, Dehradun. Okay. Next is Institute of Engineering and Technology, Dr. B.R. Ambedkar University. Hello.
सिस्टम में से लग रही होगी स्पीकर के लिए सिस्टम में सीपीयू से
40 participants are there. Okay, fine. No, B.R. Ambedkar. Next is Banasthali Vidyapeeth University, Rajasthan. Now I invite JCDM College of Engineering, Sirsa, Haryana.
Hello,
JCDM College of Engineering, Sirsa. Yes, your voice is coming. Your mic is off. Please switch on your mic. Your mic is switched off. Please make it on. Go to settings and then make your mic on.
Hello.
Yes.
Yeah.
Yes, please.
Dr. Mehra, good morning.
Good morning.
Yeah, thank you for inviting us with such a great opportunity for us to join this VLSI design program. And we have around 32 participants from computer science department, electronics and communication, as well as from electrical and electronics department. So the content part is really very good, and it's a very well opportunity for the staff as well as for the students to develop and to learn something good about the VLSI design. The experts are really very good. They have very good command on their subject. So thank you very much for giving us a wonderful opportunity. Thank you very much.
Thank you. Thanks a lot. Now I invite NC College of Engineering, Panipat. Good morning. Please go ahead.
Our chief is Mr. Dr. L. Curtis. Next slide is from DRDO. The targeting is the coordinator for the workshop. There are also 14 faculty members on this platform. I hope this will be
Thank you. Thank you very much, Professor. Next is Gyan Jyoti Group of Institutions.
Good morning, Dr. Rajesh Mehra and
Good
your
morning.
team at NITTTRCHD, Chandigarh. First of all, we would like to extend our warm gratitude for providing us this opportunity to conduct this online program on VLSI design. Around 20 faculty participants are with me in this room with some of the student participants also. Now, this opportunity provided to us by you would definitely of great help to our faculty member as well as staff. Reason being is that VLSI designs are being used nowadays in almost every kind of home appliances. We believe that nowadays word without VLSI is word is not enough. We strongly believe that whatever input we'll be getting from your expert in this VLSI design workshop would definitely of great value addition for our faculty as well as staff as well as students. So I hope our journey in this direction would definitely take a great step with your kind support and expertise that you have in on this subject. Yeah. Thank you, sir. Thank you.
Thank you. Thank you very much. The next one is ICLIT Ambala. Okay, this is disconnected. So next center is AIT Tonk, Rajasthan. AIT Tonk, Rajasthan. Can you hear us?
तो अब आप लाइव कनेक्ट हुए अब
Good morning, sir.
अब आपका फोटो भी आ रहा होगा आई थिंक कहीं
A very good morning to all the faculty members of NITTTRCHD Chandigarh and the participating colleges. Asian Institute of Technology, Jaipur feels privileged to be a part of this program. This is the third time we are being organized this program, and the number of participants are 30. And I would like to transfer the mic to our sir, Mr. Dharmendra Kumar.
Good morning to all of you. Welcome to all of you at Asian Institute of Technology. Myself, Dharmendra Kumar, Head of Department Computer Science and Engineering. Regarding this institution, that since its inception in 2009, Asian Institute of Technology prides itself in understanding its responsibilities towards to giving the students the perfect academic training and atmosphere. Located on the serene and outskirts of the Jaipur-Kota highway, the institute is approved by AICTE and affiliated to RTO Kota. It is a learning zone where students are taught to become a man of value, not man of success. Thank you very much.
Thank you very much for sharing your views. Next is Mewat Engineering College, Haryana. Mewat Engineering College.
Good morning, sir.
Good morning.
We are very thankful that you have accepted our invitation. And here we are trying our best to invite Jamia Millia University faculty as well. And Al-Falah University and Mewat Engineering College, which is adjacent to our college. And presently, our computer science department, electronics department, and electrical engineering department is participating, and our student also.
How many participants are there in your center? How many participants are there? Registered participants.
Registered participants are 20 at present.
Okay, thank you very much. Next is MIT Muradabad.
Morning, sir.
Good morning.
We had around 40 number of total registered participants. 40.
40. 40, okay.
4040. And I hope this course will be beneficial like the previous one. We had already a part of the previous courses. And we wish you all the best. Thank you.
Thank you very much. Next is our Universal Polytechnic College, Laladu. Universal Polytechnic College, Laladu. Your mic is on mute. Kindly switch on your mic, please. Universal Polytechnic College, Laladu. Switch on your mic. Go to settings and switch it on. Your voice is not coming here. Okay, please. Yeah, now it is coming. You can go ahead.
Logic.
Yes. Universal Polytechnic College, Laladu. Okay, next I invite GTBIT Delhi. GTBIT Delhi, can you hear us? Okay. Next is Thapar Polytechnic College. Then Indira Gandhi Delhi Technical University for Women, Delhi. IGDTU Delhi. Good morning.
Good morning to Dr. Melvin Dutta also. And we at IGTU are very happy to be a part of this endeavor of NITTR Chandigarh. This is the first time that we are conducting this HTC and VLSI design. And on the behalf of the entire organizing committee, I thank you very much for considering us. And we look forward to a fruitful session with the experts in the next 5 days to come.
Thank you. Thank you very much. And now RD Engineering College, Ghaziabad. So this is all about our RD Engineering College. Can you hear us? Please go ahead. So this is all about the introductory part of our program, and now we have with us Dr. P.K. Tulsi, Dean of NITTTR Chandigarh, to grace this occasion. So I request Dr. P.K. Tulsi to kindly address the gathering.
Thank you, Dr. Rajesh Mehra. Good morning, everyone at the various centers which have networked with us for the program on VLSI. And on the behalf of Institute, I extend a hearty welcome to all the directors, the dignitaries, the invited guests, and the participants of the program. And I compliment the Department of Electronics and Communication Engineering, and especially the coordinator of the program, Dr. Rajesh Mehra, who has put an effort to connect with 28 centers across the country. This is actually giving us encouragement because the purpose of integrating information and communication technologies in training of teachers can be achieved if we have 20 or more than 20 centers, and we are catering to the audience more than 500 at a particular point of time. As rightly said by many of the experts, this particular area has wider application, and I'm sure the next 5 days will be very interactive, and the faculty members and students who are attending the program, they'll immensely benefit through the interaction with the experts who have been invited for the various input sessions. We have few centers which have connected for the very first time. So I would like to just give you a brief orientation regarding National Institute of Technical Teachers Training and Research. NITTTR, as we refer to it, was established in the year 1967 with the sole purpose of improving the quality of technical education, especially at the polytechnic education level at that point of time. And in 2003, recognizing the services of the institute in the 5 major areas, the status of the institute was elevated to national level institute, and that's why it is now known National Institute of Technical Teachers Training and Research. The institute undertakes 5 major activities, which include education and training, curriculum development, instructional material development, research and development, and the 5th major activity is extension and consultancy services. Under education and training programs, the institute offers 6 master's degree programs, which are 5, out of which 5 are in the basic engineering programs like civil engineering, electrical engineering, electronics and communication engineering, computer science and engineering, and mechanical engineering. The 6th program is interdisciplinary, which is MTech Engineering Education, with a 50% focus on educational technology and another 50% on educational management. These programs are being offered by the Institute on 2 modalities. One is the regular contact-based programs, which are of 2.5 years, and then we do offer these programs on a modular basis, where the teachers from the technical institutions join us during the summer vacation and the winter vacation, and for 35 days they are with us for undertaking 2 courses of study, and the examinations are common with the regular contact-based program, and these programs are affiliated to Punjab University. The best part of these programs is that under the leadership of the present director, Dr. M.P. Punia, we have tried to network with the industry, and majority of our students are now taking up their project work in the industry. And there's a lot of focus on practice, that is in the lab or the workshop. So these are industry-oriented practice-based programs which are being offered, and the effort is also on that whatever problems are selected by the students of master's degree program, they are the real life problems from the industry or the society. Then we take up short-term training program, and the duration of the short-term training program varies from 1 week to 3 weeks. And there are about 450 to 500 training programs which are organized annually by 14 departments of the institute. We have 5 major engineering departments. Then there are 9 departments which are offering programs in the area of curriculum development, education and educational management, entrepreneurship development. Then we have rural development and so on. So there are programs which are offered to technical teachers in wide variety of areas, and with the integration of information and communication technology, the number of teachers who are trained annually, that has now been 20,000. Earlier we were able to only train 5,000 teachers in a face-to-face contact-based programs. So this is the potential of ICT. And then we develop curricula for the technical institutions, and especially at the polytechnic education, that is the activity undertaken. There are autonomous institutions which are coming to NITTTR for designing and developing the curricula. So now it is not restricted to the polytechnic education level. And attempt is made to invite industry personnel and also to develop competency profile of engineers in different branches of engineering and technology, and design curricula which are as per the requirements of the world of work. To facilitate the instructional processes and to facilitate learning among the students, instructional material development is undertaken by the institute. And we do develop print material and the non-print material. Print material consists of the books, the lab manuals, the workshop manuals, instructional sheets, as well as the course materials. Then under the non-print material, the focus is on developing digital content, and effort is being made to generate e-content in the subjects which are taught either at the diploma level or at the degree level. At present, the institute is having a major project undertaken for the state of Uttar Pradesh, where syllabus-based e-content is being generated by the teachers from the polytechnics of Uttar Pradesh. And we have accomplished this project for two, that is electronics and communication engineering branch, and then for the mathematics branch it is being undertaken, and we are likely to complete the assignment for these two branches. Then we do develop the e-content through our programs which are run through ICT. And we have now created our own web portal which is referred to as NITTTRCHD Technology Enabled Learning Portal. And the access is available on the website of the institute, and it has more than 1,000 video lectures which are available in various branches of engineering and interdisciplinary areas. So these videos can be accessed by the teachers and the students for learning the various topics related to engineering and interdisciplinary areas. And the survey which was taken up by the ETV department, that clearly indicates that the videos which are available on YouTube, they have been accessed by people across the globe, and the maximum hits on a particular video are around 70,000. So that is very encouraging figure for all the faculty members of NITTTR, that their work is being recognized and people are actually taking benefit of the work done. Then we do take up R&D, and there are two types of research and development activities. One is in the area of engineering and technology, especially the faculty members from engineering branches. They are taking sponsored project from Department of Science and Technology, Department of Communication and Information Technology. Then they are taking a project from Ministry of Social Justice and so on. And these projects are being undertaken either by the faculty of NITTTR or in collaboration with institutions of higher learning. And in addition to that, the ME dissertations are taken up by the faculty. They are supervised, and 70 teachers, they are pursuing their PhD work under the supervision of the faculty of this institute. We are a recognized research center for Punjab Technical University and Punjab University. Then we do take up research in the area of technical education, and this is where we have already taken up number of projects sponsored by World Bank, NPIU, and also EDSEL, and then we are taking up projects sponsored by directorates of technical education in the state of northern states of the country, and we are also taking up studies to review the programs being offered by NITTTR. So at present, two studies are going on where we wanted to evaluate the effectiveness of our programs so that we can improve upon the quality of our short-term training programs. In addition to that, another study which NITTR has taken up is the impact assessment study. So we are trying to analyze the data, so what impact we have made on the technical education system, and there we are gathering perceptions of teachers who have undergone the program from 2008 to 2013. Then we do offer extension and consultancy services. These are need-based, customized training programs, customized R&D, or customized instructional material development or curriculum development projects being undertaken by the faculty of the institute. And these services are offered sometimes free of cost, otherwise they are paid services which are sought by the technical institutions in the country. So these are 5 major activities which are being undertaken by the institute. Institute is also gearing itself towards offering massive online open courses, which the project is being coordinated by Indian Institute of Technology, Mumbai. So these, I would say, at the end, again, I would like to congratulate the Department of Electronics and Communication Engineering for offering this program where we already have a success story of 20 institutions joining first time, 22 joining in the second program, and this time 28 institutions have shown interest in networking with NITTTR for the VLSI, and I hope this particular program will be a great success with the collaboration with SCL Mohali, IIT Roper, NIT Kurukshetra, and Cadence Industries Limited. So with these words, I wish you all the best for the next 5 days, and I'm sure that there will be useful outcomes of this program. So thank you very much.
Thank you very much, ma'am, for your best wishes, for encouragement, and for your unconditional support every time to us. And now we are just at the end of this inaugural session. At the end, I extend my vote of thanks to Dr. P.K. Tulsi, Dr. Maitri Datta, dignitaries at different nodal centers, local coordinators, participants, our ETV staff for their full cooperation and support. So this is all from our side. Now we are going to start our first session after a break of 15 minutes. So you can have a 15-minute break for tea. Then we will start with our first session on
नहीं नहीं रुको ये जमाने का जाएगा
जो जिस फॉर्म में मांगा है उन्होंने भेज देंगे। हैंड रिटन मांगा है, साइन मांगा है, टाइप करना, साइन कराएंगे उसका। नीचे वाली लिस्ट में हम लोग कौन से हैं? वो ये हुए भी वहां से ऑफ है क्या हम लोग? हम किए वो कहते हैं अभी वो उनका बंद है। अभी तो बताया ना, मेहरा जी जिस तरह का अरेंजमेंट किए वही जाने लायक है। हम लोग ज्यादा सिंसियर आगे बैठ गए।
सारे ज्वाइन है सेटिंग करा खाली दूसरी आ रही है उससे ज्यादा हाँ जी ठीक
Can I start? Good morning, dear participants. I once again welcome you all after this tea break. Now we have with us Engineer H.S. Jatana from SCL Mohali. Engineer H.S. Jatana has received his BTech with honors from BITS Pilani and worked with CMC as software engineer. Later on, he shifted to SCL Mohali and presently working as head VLSI division. He is actively involved in ASIC and standard IC design for ISRO and other departments. His contribution to VLSI world involves testing of 6502 microcontrollers and peripherals, 12-bit ADC, timing ICs, etc. He worked at Rockwell Semiconductor USA and AMS Austria for porting of 2-micron CMOS processes. He managed many important projects based on CMOS imaging sensor, RF CMOS, SRAM, etc. His interest areas are low power design and low voltage analog design, along with development of CMOS MEMS integration processes, HV CMOS process. He is also responsible for training of engineers at SCL. He has delivered many expert talks related to VLSI design at ISRO centers, DRDO, CSIO, IITs, NITs and PUs. Now I request Engineer H.S. Jatana to kindly continue with his first talk on CMOS design. Jatana ji, please.
Thank you, Dr. Rajesh Mehra ji, for the nice introduction. So we will start with this talk. My voice is clear, audible to all centers? You can please कीबोर्ड कहाँ है इसका? Keyboard. How to address this? It is through this? Okay. No, I think it's okay. Now I got. Is it visible to you? Okay, so we will proceed with the analog design. So I just before we proceed with the regular lecture, I will just talk around 5 minutes. What is an integrated circuit design? Integrated circuit, as you know, it means designing of a complete circuit using various components which can be active or passive on a single substrate. So all single substrate means there should be a common platform and all those devices are manufactured together, so that there is not a big board, it's a small size. There are certain advantages of doing this, which I think all of you are aware. So there is a digital design and a concept of analog design. Now I will be talking about in this lecture mostly about the analog design. So what do we mean by analog? Analog design means we have to design like what are the circuits which are analog in nature. This whole word is analog, and if you see the like voltage regulator, power supplies, filter, and all these things,
ये
100% कर दीजिए ना
लैपटॉप यूज कर
लैपटॉप से अच्छा ओके
कम कर दो माइनस से बंद
इसमें भी तो पीपीटी की ऑप्शन होती है
थोड़ा सा और
ये इधर से करो इससे छोड़ो इस वाले से देखो
पीपीटी देखें
पीपीटी है
पीपीटी भी है वी कैन ट्राई दैट
पीपीटी खोलो
पीपीटी
ठीक है
मेरे को लग रहा है पीपीटी आई थॉट दिस इज बेटर
F11
दिस इज ओके
yes
कहां पे जाएगा मैंने स्क्रीन शॉट इससे पीछे एकदम
okay now it's okay so what I was talking is there are two broad categories one is a digital and another is an analog you see this world is in analog world so if you go back around 20-30 years back most of the circuits were analog in nature and then when the digital came there are certain advantages in digital because of noise margin if you have to transfer data from one point to another point earlier we were doing by using an analog data like a voltage is being transferred say if the voltages levels are high then it's okay but if the voltage levels are very low say 200 millivolt so there will be some interference some noise in the line and on the receiver side 200 millivolt will not be received as 200 it will be received differently so your signal changes so it's very difficult to transfer an analog signal from one point to another so then people thought this is how the digital thing came which has a better noise immunity so you are transferring a logic 1 and 1 can be anything as long as it is more than say 2.5 volt to 5 volt in that range it is treated as logic 1 only so this there are certain advantages in when we are transferring the data and digital another advantages is your algebraic calculations and use of computer we all know there are digital computer to realize a big circuit using gates is very easy as compared to the analog calculators so but now the word is an analog so data crunching job and whatever you have if you have to do some calculation we would prefer to do in a digital thing but then from the word we are getting the signal which is analog so you should have an analog to digital converter also then it will convert to a digital data manipulation will be done by that circuitry using gates and the output also has to be given to the word which you need and like to the which analog signal so then you need a D2A also so that it converts from the digital to analog and so that is how their A to D, D2A, so these are the crucial blocks of analog. Then whole system has to be given a power supply also. So it needs power. So there are power management chips, which gives a, if you see that today's even a microprocessor from an outside there is a single supply which is coming maybe a 5 volt or 10 volt. But inside the chip there are many supplies, maybe 1 volt, 0.5 volt, 1.5 volt. So all these things you cannot give some 5 supplies from the outside. So from the outside only single supply is given and all these other power supplies are generated inside the chip. So this is how the things are done. So that is a power management is a, even if there is a digital circuit like microprocessor, microcontroller, they are purely digital in nature. But then again there is a good analog component which is sitting on a digital chip because of doing this power management. So now today we have to cover this analog design and the basic element of any design is a MOSFET. Now here analog, what are the components which we are interested, which we need to design any circuit, electronic circuit? You need active component, you need passive component. What are the passive resistors, your capacitors, inductors, and then diodes, transistors, right, varactors. These are the, broadly speaking, these are the ones. Now the beauty of using MOSFET is MOSFET can be used as a resistor also, it can be used as a capacitor, it can be used as a diode, it can be used in a certain configuration as an inductor also, as a varactor also. So in a big circuit, you will find the symbol of MOSFET only, but that doesn't mean that that transistor is always used as an amplifier. At some places it is amplifier, at some places it's just a switch, at some places it's a resistor, at some places it's acting as a capacitor, at some places it's a dummy, it's doing nothing, it just because of some reasons it is sitting there. So at some places it's a diode. So all these things, you see, analog design is a very simple analogy. Is like a 7-year-old kid. There is a game, some mechanical, some components are there, and the kid sees the picture and connects these components in a way to make a building. So he connects in some other way. There is some other shape is there. So that kind of game toy are available. So the same kind of concept is here. So there are different blocks. You have to interconnect those blocks. In a mechanical thing, how you can interconnect? There is a groove and it will lock inside each other. So, but what is the locking in electronics? Different blocks, your voltage, your timing, it should match. Your voltages should match. That is how you can connect. So in any analog design, so first of all, then what we have to see, what are the various combinations? What are the various configurations? So we have to understand those configurations. So how they can be applied, what is the functionality of those configurations, and then how those configurations can be interconnected to make bigger and bigger circuits. So first of all, I will just go through this MOSFET only very in a fast manner, because this is the basic structure which you know, and this is the symbol here. Okay, so this is the NMOS commonly used here, and this is the P. So but we use an arrow here and an arrow here in case of an P, and not this kind of dot here. So in some books it is mentioned like this. So but and complementary means these P and N are manufactured, are joined together, or they are produced together. Now the cross section is very important to know. Now you can see, because this is just a symbol, and when it goes on a wafer, it will be, the layout is different. So we have to understand how it will look. So this is how it will look. So you can see here, this is the source drain, this is the source drain, and this area, this is the top view. From the top it looks like this. So this hole is the gate here, and this is the channel length, this L, and this is the W. This is the W of the transistor, and this is L, this is source drain, this is source drain. And now you can see this. So from here you can see this here, this is a silicon dioxide, this one crossed this XX you are seeing, this is the poly line, this is the poly, and you can see this is some dielectric, because then after we are covering this. So this is the gate, this is source, and this is the drain. So this N plus for making this contact. So these are the metal, these cross lines are the metal lines, these cross lines are the metal lines here, right? So this is metal, this is metal. So contact of this metal is made here, and this metal is made here, and all these kind of dotted, these are all oxide dielectric. So here it's a field oxide, this is a gate oxide, and this is field oxide, this is field oxide. So we have two contacts, and this is now another view is, this is an exploded view. You can see here, this is the source, so we have to make a contact of source. This is a symbol of contact. So this contact, if you see, it is raised here, and this is the metal line. So first a contact is made, and maybe contact is filled with cobalt silicide for better conductivity, and then a metal is put over, like some aluminium or copper. Then this rectangle, this represents a metal. Similarly here, this is contact, and this represents the metal. This is the gate, and gate, we normally, you can see here the channel will be here. So we are not making the contact here on the channel, but here this area where we are making, this is the contact we are making here for the gate. So this area lies on the field oxide, it is on the top of field oxide. So we are making contact over field oxide, so that this we don't want to take any chance if we make any contact here, because below the channel is there. So we don't want to disturb that. So the gate above the channel is not disturbed. So contacts are made here. So this is the contact, and you can make a poly contact also, or you can make a aluminium contact. So this is how, when you do the layout of the transistor, this is how it will look like. This one, this whole thing. So this is the cross section. This is the top view of the transistor. Okay, so this is the same thing, but in a 3D kind of picture. So this you can see, this is the W, this is the width, this is the L, and you can see here, from now we are seeing this picture from the side, from this side. If you see from this side, you can see, as I told you, this this is the poly, this poly gate. It goes above your feed oxide, and we make contact here, because this is the channel area. This from here to here, we won't make contact here. You can see this here, it is shown the contact is made here. You can make it here also, or at both places, it doesn't matter. So we don't make contact here. This is raised. There are reasons for that, due to bird speak and all those things. This we will not cover in this, but this is how the actual whole thing, 3D picture of this particular transistor looks like. And as you are aware, P and N, they are manufactured together. So this is how it will look like. You can start with P substrate or an N, and side by side you can make both the transistors. Now this operation of MOSFET. Now first thing, for any design, it is very important to, there are two things. It's very important to understand the device physics and to understand the model, because everywhere these models will be used. Now if you see the model, there are levels, level 7, level 17, level 41, BSM 3v3 and things like that. So a transistor like the model which we are using, 3v3 model, it has around more than 130 different parameters. But that if you have to use that, definitely you will need some bigger computer for that. But that is not required. We start with the basic equation, which is all of you are aware, mu naught C ox W by L. What is that? Mu naught Cx W by L VGS minus VT square 1 plus lambda VDS. So that basic equation is good enough. Only it takes into account the first order things only, and second order effects like short channel effects. 1 plus lambda VDS you multiply. So that equation is good enough for understanding these circuits. Now you see here, what is the operation of this transistor? So the operation of this transistor is, if the transistor will be normally off, if we have to make it on, a channel has to be established here. And how you can establish a channel? You have to give some voltage, VGS. Okay, so you have to give some gate voltage with respect to source. You see, this transistor has 4 terminal actually. Body is also a terminal, but only three are shown. So any terminal can be taken as a reference or a ground. In this picture, I am using the source as a reference, because all these voltages are with respect to this. This is the common voltage, 0. It can be any volt, it's source volt, right? So all voltages, because voltage is with reference to some node only. Okay, and ground we say 0, then all voltages we define. It is like that. So here, if the voltage at the gate is more than the threshold voltage, then the channel will be established. But that doesn't mean the current will start flowing. Okay, the channel is there. What is the meaning of channel? Channel means this area under the gate, that is inverted. Inversion occurs. Okay, so again, I will not go much in the physics of this, but this a channel is established. So it's an N device. This means there will be an electron, mobile electron charge on the channel. It's filled, completely filled here. This area is completely filled. But when current doesn't flow like this, then what you have to do is you have to raise VDS, because current cannot flow, because the potential. Current will only flow if this potential at drain is more than the potential at source. So if VDS increase slightly, 100 millivolt, 200 millivolt, the current starts flowing. Okay, so this is the, based on this, you can plot, you can vary the value of VDS, you can vary the value of VGS. So these diagrams, they can show the various values of VG and VDS, you can see here, this is the formation of the depletion region. So first the depletion region is formed and then the inversion is formed. If you increase VGS, if you keep on increasing VGS, then an inversion layer is formed, the sea of electron which you are seeing here, this one. These are the free electrons. These are ionized atoms only. These are depleted. These are ionized atom. But ionized atom, they are in a lattice. They cannot move. Okay, that is why it's known as a depletion. Depletion means it is depleted of charge carriers. There is a charge. Region is charged, but charge carriers are not there. So they cannot. So and when you increase the voltage more here, then what happens is, because the charge neutrality has to be maintained. So there is some charge here. There is some charge which is available here. We have a mouse here. It's better. Mouse is there. There is some charge here, and if you increase on charge, then the equivalent number of charge has to be here also. So that is how these electrons will come from here. This is a lot of electrons are available here. So these electrons will come here and they will sit. They will make a sea of electrons in the channel. That will be better slightly. Yeah, that is good. Right, so then sea of electrons will form. So these electrons. Now if you raise the potential at the drain side, now what happens? These electrons will start moving. So this is here. If you apply the drain voltage, then the electron will start moving in this direction. It will be attracted and a charge flow. So this is how the channel formation and these curves are very, very important. You see what these are the two curves which we call as a transfer characteristics. There are three things which are important, and if I tell you, you see there are three things. This is a transistor. This is the common voltage. This is the input side. This is the output side. So what we are interested in input characteristics, means this current I versus VGS. What are input current, which is IG versus VGS. Then we are interested in output characteristics. What are output characteristics? This is IDS versus VDS. So this is IDS versus VDS. And then we have a transfer characteristics. Transfer characteristics means how the output is related to the input. VDS versus, or you are think IDS versus VGS. So these three characteristics you have to understand very clearly how the transistors. So now this is ID versus VDS. So this is what ID is also from the, you can see from here, this is ID and this is VDS, right? So this forms this ID versus VDS. This becomes a output characteristics. ID versus VGS will become a transfer characteristics. Okay, so this is important. Here you can see this. Let us see. So this ID versus this is VGS. So this is the point. There will not be any current, and then the current starts flowing. Okay, so this means the transistor starts flowing at a voltage which is more than VT. So this point is VT. So if you vary VGS1, you will have different curves like flowing like this, right? And if you plot, this is output characteristics, means this I0 or IDS versus VDS. Actually this is versus VDS. So these kind of curves you will see, and this is the saturated voltage which is known as VD sat.
Sorry,
VD sat. Yeah.
So the lower portion of the slide is not visible.
Okay. Yeah, it is.
Like the saturation is the curve. It's not visible completely.
या तो यहीं से फिर करना पड़ेगा
कुछ हो सकता है सॉल्यूशन बताओ मैडम We are working on that.
Okay, we are working on this. Maybe it will improve, right? But these things you can see if there is not clarity. Now these are available on any textbook. What I am making is you should be very clear about the input, output, and transfer characteristics of the device. So these things I will skip because only thing I will give you a brief everything I have mentioned that, and you know all these equations also. So this is the main equation that ID is proportional to VGS minus VT square, right? This is ID is proportional to VG minus VT square in the saturation. In this, when the transistor is saturated, like the channel pinch off has occurred, then the ID current is proportional to VGS minus VT square. This is a technology factor, mu naught Cox by 2 into W by L. So K dash is mu naught Cox. Though this equation, if I explain here, you see the transistor, there are three regions. One is the cutoff, then triode, then your saturation. Now, if we plot, say, IDS versus VDS, what happens is, if VGS is less than VT, if VGS is less than VT, there won't be any current. The curve will be like this, no current. Okay, so this is the cutoff region. And if VGS is more than VT, then the current starts flowing. It will be like this. So this is at some VGS1, and if the VGS, if you increase, then it will be VGS2. If you increase more, then it will be VGS3. Like this, it increases, and these are the values here. This is VD sat, where the value get saturated, and you can see this is almost a linear. So this is known as a linear region, and this is known as a saturation region. And the equation which ID is equal to mu naught C of W by L VGS minus VT into VDS minus VDS square half. This is for the triode region, and for saturation it is W by L into 2 VGS minus VT square. So this equation becomes the very basic equation, and for any circuit topology, if you use this equation, you will get the correct results. Now the question is here, another thing which is important, if you are able to see this equation VT, because VT also changes with body bias. VT is not fixed. What do we mean by body bias? Like if this is the transistor, if this is the body, if this body and this source and this body are at the same voltage, if they are at the same potential, then the threshold voltage is VT. But if there is a potential difference between these two, then the threshold voltage will also change. Okay, so this thing will occur, then VT will change, and that is the equation. How it occurs? If you are connecting two transistors like this is VD. So now you have connected two transistors. This body you have connected to ground. This body also you have connected to ground. Here the source is connected to ground, body is connected to ground. But for this transistor, body is ground, but source is not ground. It has some potential, so it will get a VSB. So its VT will also change. VT will increase depending on the VBS. So these things you have to keep in mind, and this is the equation how much the VT will change, and otherwise these equations are same only. And you see, now let us go for a simple MOS transistor model. So because for any circuit, whether it's a digital or an analog, we should have a model of the transistor, otherwise we cannot solve that equation. So what is that simple transistor model? Simple transistor model is like drain current. We are saying that drain current of a transistor is proportional to VGS minus VT square. You can see here it is proportional to VG minus VT square. This is 1 plus lambda VDS is because of channel, and it can be left for some time, you can ignore this. It's a, if lambda is normally very small, so it can be ignored also. And this k mu naught Cox is the technology parameter. You cannot change. This value is fixed. So what is in your hand? You can change W, you can change L, and all voltages, VD, VGS, anything you can change. So for a circuit designer, he can change all voltages, all transistor voltages, and the physical dimension of the transistor. What is that? L and W. He cannot change mobility, he cannot change Cox. That is dependent on the, that values are given by the technology. So that he cannot change. So now you see this now simple equation, gate to source voltage and effective gate to source voltage are respectively. So this, if you manipulate this equation for VGS, you will get these kind of terms, VGS also, ID versus VDS and ID versus VEGS. So these equations, you just a simple manipulation, and similarly in the triode region as and in the saturation region. So all these different equations you will get. So now, but I will just give you a summary of this. If you are able to see, so what is the simple model of a transistor? So the very simple model of a transistor is, we can assume the transistor to be a current source, which is a voltage dependent current source. Like, so this is a controlled source which is dependent on the input voltage. So if this is VGS, so this will be GM into VGS. This is the, and this is V0. So this is drain, this is gate, this is source, this is grounded. Okay, so this is a very first level of very simple model of a transistor, which assumes transistors to be a controlled source. It's a controlled source, and the value of the current is, it's a current source, and the value of the current depends on the input voltage VGS. Now this is the first level. If there is any circuit, you replace that circuit with this model, and then the circuit becomes linear. You can solve. Then you will have only linear equation you can solve. And after that, the second level is, you have to, because of channel length modulation, there is some resistance which is coming, which we are calling as a G0 or R0 or GDS or RDS. So this term will come. So there are three conductances in a transistor. First is the mutual conductance, which is GM. Then there is an output conductance, which is R0 or G0 or RDS or GDS. Different books write differently. So that is the next conductance. And then there is another conductance. What is that? That is a GMB, where GMB, here we are assuming source is at ground. So body and source are same, but if body and source are not same, so their body is at a different potential than source, then GMB will also come into picture. So in more complex cases, GMB will also come into picture. Okay, so this, now you see, this is some circuit. What it does is, this is, if you see M1 and M2, they are it's a differential amplifier, M1 and M2, and this M5 is a current source, and this M3, M4 are a load of this active load. So this is a differential amplifier. So if you give any input here, like this is this input, and for this stage, and this input for this, now they are actually common voltage is being given to this, but you can give separate input also. And here we here output, what output will GM-R0, the output will come GM-R0, where GM is GM of this M1 and M2. M1 and M2 are perfectly matched, they are the same transistors. Now this output will come GM-R0 only when all these transistors are in saturation. So you have to ensure, you have to make these transistors, in such a manner, you have to ensure that all these transistors are in saturation. So how you do this? You see, for doing this, this M5, you see the condition is here under balance condition. Now, if the circuit will be balanced, if this input is equivalent to this input, both inputs are same. So then what happens is, here there are two paths. One path is this, another path is this. So same current will flow here, same current will flow here. So both these current join together and come here. So this means if I5 is the current in this M5, so here current will be I5 by 2 and here current will be I5 by 2. Okay, so now if this is I5 by 2 and this is how I am generating this current, this is some I0, and with this transistor I am generating this source. So this M6 and M5 have to be matched together like this. Okay, so W and L of 5 and 6 should be matched. So that way you can, this I5 current can be generated by using this I0, IB or I0, whatever you call it. And here you have to ensure that all these, when we analyze differential circuits, we will see we have to calculate the voltage here, we have to calculate the voltage here, what is the swing of the voltage, how low and how high it can go at this node, so that these transistors remain in saturation. This remain in saturation. This, what is the condition for a transistor to remain in saturation? There are two conditions. One is the VGS should be greater than threshold voltage, and another is, what is that? VDS should be greater than VGS minus VT, or VGS minus VT is known as overdrive. So you have to see these two conditions and for each transistor and ensure that all these transistors are in saturation, then only here your actual result will come. Otherwise the result will not be actual, because the gain will fall. If the transistor comes out of saturation, if they are in the triode region, the gain starts falling. So now, as I told you, analog design means we have to learn a few circuit configurations, very popular circuit configurations. I will demonstrate here the main one, and you see here the first one is a common source. So this is a, what is a common source? Source is common, and this is a okay, common source is not coming, it's a common gate amplifier is coming first. So it's basically, you see, it's a common gate. So gate is a common terminal. So we are applying input here. What will be the output here? If I apply, this is an I bias, because to put this transistor under a stable operating condition, under saturation, you need some biasing. So this circuit represents the biasing. So I have given some I bias, and now the circuit is biased, and this I supply, I bias and I supply will be same if no input is connected. But now I am connecting an I source here. So what happens is this IS is connected here, at here. So I am feeding IS also. So this IS and I bias, it will be added. This is a current source. Any current source will have source resistance RS. That is how it RS is there. So IS will get added into this, and what will be I out? Then I out, the same IS will come here, I out. Okay, because the source and drain current have to be matched only. Okay, even if there is some confusion in this, then what is the thing? You make a model of this. You draw that model. From there, you will be very clear. Okay, so now because in a transistor model, what we are doing is this gate is ground. Okay, so now if I take some current at the source, the same current will come at the drain only. Okay, because the drain and the source current are same, so they will come at the same level. And at this point, if I connect a load also, so this IS will come here. So I out will be equal to IS only, the source current. So this is how, under this, now this is the AI is I out is equal to ID, which I told you, and this is same thing is being drawn by using a model. Now here you see GMB is coming. So as I told, there are three conductance, GM, G0. This is G0. Here R0 is written. You can write G0 also, or R0. This is G0. This is GMB. Why GMB is coming? Now you see here, source, this body. This is the body potential. Body is not connected to source. It is V. If you connect body to source, then GMB will not come. So this body is because this source is lifted. Body is at, this V is at 0. But this is source. Source is not at 0. Okay, this voltage is not at 0. It's not ground. There is current source also here. So this is not ground. So that is why GMVV is coming. So this potential is not 0. If this potential and this potential are same, so it will not come. So now you can see this GMVVB is also coming, GMVGS are not, and this I out. So if you give IS here, I not here, because at this node this current is entering, and whatever way this current is divided here. But what is this current here? This current is this plus this plus this. Okay, which is this only. So IS is equal to I naught here. Okay, so current gain is -1, but of course in the direction will reverse. So this is a -1. So this is, and another thing is, you see what we do is in any block we have to know current gain, voltage gain, input impedance, output impedance. Why? What is the reason for this? The reason for this, if you know this, when you connect this block, you should know what is the input impedance. As you have seen the matching theorem, if some voltage has to be transferred, then the impedances should be equal, then only the maximum power will be transferred. So you cannot connect just like if the input impedance of that is different, here input impedance is different, so proper signal will not be transferred. So that reason we should know the input impedances also. So but then how to calculate input impedance? Now you see this is the circuit here. So input impedance means what is the impedance or a resistance. This is the input side seeing at this side. This is the side seeing at this side. So how I can do this? Again, it is very simple. I will connect a source voltage here, VT, test voltage, and find the current like this. Or what I can connect a source voltage VT, find the current, divide by 2, VT by IT. That is the input impedance. Or what I can do is I can force a current IT and measure the VT. Okay, so if I force some current here IT, so what it will be, this IT, this current will be equal to this current plus this current plus this current. This is what it is written, and opposite sign, because this arrow is here, this arrow is here, minus sign I. So what is this current? Minus GM VGS. What is this current? Minus GMB, minus GMB VBS. VBS is VT only, B and S, right? VBS is VT only. So this, and the, what is this current under this R0? This voltage is VT. From here to here, this voltage is VT, and this voltage is V0. So across this, what is the voltage? VT minus V0 divided by R0. This is VT, this is V0. Okay, so this current. So this is IT. Now you can connect these. You can rearrange this term. You can find V out. And what is V out? So V out will be the voltage at, what is the voltage here? The voltage here will be equal to ID, the current flowing, and ROC parallel with RL, this one. Okay, at this node the voltage will be ROC parallel R0. Okay, so this ID, and this ID is IT only, this one, because this current is same as this current. Okay, so this current gets divided in 3 branches, and when it comes here again, it is added, all 3 branches. It is same at this. So this V0 and this IT, so you can eliminate V0, and this expression will count in terms of IT and VT. So you divide VT by IT. VT divided by IT, you will get the input resistance, which is like this. So this you will get a term like this. Okay, and this is the thing, GM plus GMB this, and for approximation, GM plus GMB is much greater than 1 by R0, and R0 is much greater than RL. So you will get RN as 1 over GM plus GMB. So this is you will get, and if GM is high, then RN will be low. Okay, so now what we have achieved in this, the input impedance is very low here. We have achieved input impedance low, and in the same way you can calculate the output impedance. Output impedance will be calculated at this. This is the output node. So output impedance will be calculated here, and same way VT/IT, if you do, you write the same equations, current equations at this nodal, you will get VT by R0, which is this, and you can see here the output impedance. This is the equation for output impedance, GM R0 plus GMB R0, and this. So what it means is, you see what we have gained. What we have gained is, if I have a current source here, IS, if I am if I want to use directly as a current source, it will have some input impedance which is RS. But for a current source, what is the input impedance? You need a very high impedance for a current source. What is the reason? What is the reason we need a very high? Because we want all of the current to go to the node. You see, there are two. Even if I have a current source here, this is I0, right? If I am connecting this and this is RL, say RL is equal to say 100k. This is the current. So the entire current will flow through this. Okay, if its impedance is infinite, but normally there is nothing like infinite. You will always have some impedance. So if this impedance, this is the impedance, but say this impedance is also 100k. So if this current I0 by 2 will here, I0 by 2, only half of this current is going here. You got my point? And if the load is say 1k only, the load is very small, then no, if this is 100k, this is 1k, then more will come. But if this is high, very less amount of current will flow. So what we want to do is we want this R to be very, very high. We want to increase. So how we can increase? By using this configuration, by using this here I am putting IS, this is grounded, and if I connect here I0, this circuit RL, so here what is the impedance here? Now this IS is same, this RS. If you see the output impedance, here it will get multiplied by GMRS. From here, if you see that equation, output impedance, which is this equation which is coming here, if you see this one, GMR0 into RS into GMR0 plus GM. Okay, these terms, if we ignore all these things, because this will be small as compared to this. So this RS is getting multiplied by GMR0 RS plus RS. Like this, there are plus GMB term also. So let us ignore this. Even also we are getting, this RS is getting multiplied by GMR0. What is GMR0? That is the gain. Okay, so if the gain is 100, so it is getting multiplied by 100. Plus some additional terms are also there. You leave that. But still your output impedance is getting multiplied by the gain, which is 100. Right? So if you, instead of using this, you use this circuit, so what you have achieved is, you have achieved a better current source. So that is how in the circuits where we need that current source was imperfect. It was not a perfect current source. So why it was not perfect? Because it has a source resistance which is very low. It's not very high. So how I can make it a good current source? By using this stage. It will increase. It will not give more current. It will give the same current. And in fact, if you see the actual thing, it will give less current. It will be some 95-96% only current it will give. But what is the advantage? Advantage is its impedance is getting multiplied by gain. It is becoming a perfect current source. So this is how the advantages, these are the various calculations. Actually in this thing you have to proceed step by step and do all these calculations. Then only you can realize the beauty of this. And where I have assumed certain values, GM500, GMB50 are not this, and then you can calculate these exact values. You will see how much difference it becomes, and it's very easy to calculate. You don't need any tool for this. You can calculate very simply, easily. So now this is the model for this. So how we can represent? We have found input impedance is 1 over GM. Right? You see, another thing you should always remember, this is the transistor here. What is the impedance here? It is infinite. What is the impedance here? Looking into it, Rn is equal to infinite. What is the input impedance. If I ground this, I look into there, what is the impedance? That is G0 or RDS or GDS or RDS or G0 or R0. Okay, now if I see this way, what is the input impedance? That is 1 by GM. That is 1 by GM. Now you will say, how, if there is confusion, then how you can see this? How you can calculate? Again, these things, as I told you, whenever you get a confusion, what you do is you draw simple model of this. So you do 3-4 times, you do all this, you will understand very easily. You see, what is the simple model? This is the simple model. GM, this is VGS, GM, VGS. This is V0. So now I want to calculate the input impedance here. So how I can calculate the input impedance? How you measure the, if you connect a meter, a voltmeter also, what the voltmeter does? It will either connect a voltage, measure the current, divide V by I, or force current, measure the voltage, V by I. So we can do anything. So what we can do is, we can connect a voltage Vx and see what is the current drawn, Ix, and then what is the input impedance? Rn will be equal to Vx by Ix. Very simple. Okay, so now I have connected Vx. This is ground here. So what is this G? This VGS, what it will be? This is ground, this is ground, this is Vx. So VGS is equal to minus Vx. Right? You got this? So VGS is equal to minus Vx. What is this GM VGS? VGS is equal to this current source will become, I can draw like this, minus sign, I will make it up. So GM Vx. So what is this current? This Ix, this is Ix, and this is GMVx. So this means Ix is equal to GMVx, and Vx Vix is how much? 1 by GM, which is equal to Rn. Okay, so this is very simple. But if there is an R0 here, if there is an R0, then how it will change? The formula will change. It will add, you try this, it will be 1 over GM plus G0. And if there is a GMV, then it will GMV. It will be like this. So these things will add. Okay, so this, then the input impedance, here seeing this, first is 1 over GM. If R0 is there, G0, plus GMV is there, plus GMV. Okay, so we wanted, this is Rn. You see, if, okay, these things are getting added then because of that effect. Okay, so this is the input impedance. So how we can represent in a two-port network, in a two-port model will be, so IN, so again, okay, so this, if I want to represent in a two-port network, what is the meaning of two-port networks? This is the two-port network. One is some common, there is some input, this is IS, there is some output line, which is I0. Okay, and you know what is the input impedance here, you know what is the output impedance here. We know I0 is equal to minus IN or minus IS, right? What is the input impedance? This Rn is equal to 1 over GM plus GMV. What is the R0? R0 we are assuming GM R0 into RS plus RS, or we can simplify this only, GM R0 into RS. Okay, so these impedances will come here, and I0 is equal to IS is a current source, it will come as a current source, and this you can write 1 over GM plus GMV. Okay, and there is some impedance will come, which is GM R0 into RS. Okay, so this is IS or IN, and this is minus 1. This is getting I0 into this IS. Okay, so this is how it is. It is a two-port network is represented as it is clearly. It is written this. So IN is equal to here, it will be the same. I out is equal to minus I in, and this is input and this is output. And this output I have assumed that I am taking only this GM R naught RS. Okay, because you see here R naught plus GM R naught RS, this term is much more than this. So you leave R naught. Then this term is getting parallel with this. Okay, so this term is more. ROIC is much more. Okay, so this, it will be approximately this only. GM R naught R as an approximation. So what is the function of a current buffer? Low input impedance, high output impedance. We are achieving this. So how we can achieve? If you want to do a matching, okay, you want to have a particular input impedance, so you can design this stage by fixing GM. If you want some 2K, so this whole thing should be 2K. So you have to decide, you have to bias the transistor in such a manner that GM plus GMV should get inverse of 2K. Okay, so this and similarly the output impedance. So you have to do the biasing in such a manner that it gets those values. So this is now how you can design these stages. So when we do the complete design, then only we will see this. But so far we have not considered the parasitic part. We have only considered the input impedances also. As you know, in a transistor there are parasitics, and if there is no parasitics, what is the effect of parasitic capacitances? If there is no parasitic capacitance, the transistor can work at any frequency. If there is, in this exercise we are assuming current source to be a DC. It can be AC also. It can be a very high frequency current source. Pulses, high frequency pulses are coming. Okay, but if there are no capacitances, it will work. But if there are capacitances, then what happens is it will not work. Why it will not work? Because those capacitances, they need a certain time to charge. Okay, they cannot charge immediately. They need certain time. So the circuit becomes slow. So we have to understand what those capacitances are. So you can see this is one capacitance. This is source or drain. This is gate, right? And this is also source or drain, and there is an overlap. You can see this overlap. So there is an overlap capacitances, right? There is a drain. This is source. If okay, I am assuming this drain. So drain to body, source to body, gate to source. This gate to source, gate to drain. CGS, CGD. This is how it is known as CGS. This is CGS, CGD, CSB, CDB. So these capacitances are there in this. If you see, this is the source. So if you further see, this junction will be a reverse bias. So it's a reverse bias PN junction. So there is one capacitance which is known as the bottom plate capacitance, this capacitance, and there are side wall capacitances because of this. Because this also is reverse bias. So the total capacitance you can calculate of this parameter. Right, so these capacitances are there, and this is how, this is the model. Now the model will change. This is gate, this is source, this is drain. Earlier I was putting only GM VGS. Second stage was to put R naught, GM VGS R naught. Then I am putting CGS, CGD, CSB, CDB. So this it becomes this whole thing. Fine. So this is the model. This our that current buffer. So gate I have to connect to ground. Okay. So source here I am connecting a current source. This is ground. So I will have G to D. I will have G to S, CSB. Okay, CDB. So these capacitances will be there in this. Now you have to analyze this circuit by using these capacitances. Okay, so this analysis becomes, but then again it is not that tough, because using Y parameter you can write the matrix and solve very easily by this thing. So now the frequency response refers to the magnitude of the transfer function. So Bode's simplification simplifies the plotting of, I will just show you these things, I think you are all aware. I will not This is the frequency response which is given. So this is, now you see, this is a rough calculation only. This is not the exact, but it is 95% accurate. So what happens is, this is a ground here or a bias. This is the input side. This is the output side. So we will have two poles, one at the input and another at the output. So these are the two nodes. There will be one pole at X and another pole at Y. So what is that pole at X? How to calculate the pole at X? So what are the impedances at X? Impedances are, one is RS and one is of this, that is GM. So these will add. So RS plus 1 by GM. RS will come in parallel with 1 by GM. So these is the input. These are the impedances. And what are the capacitances? Capacitances, one CSB is coming and one, this is also ground, VB. Okay, AC ground. So this CSB and CEGS, though both will add, they will get added, right? So this is how it is coming here. 1 by RC. So 1 by RC is this, R will be this and CX will be, these two will get added and impedance will be RS plus 1 by GM. And similarly at Y, what will be the RL here? Load will be your load RD parallel RL load, that will come. Here he is just writing RL only. And what will be the CY? What are the capacitances? You see, one CGD is coming, right, and CDB is coming. So again, this is ground, this also is ground, VB, AC ground. DC may be at a fixed potential, but AC is ground. So these two will add, CDB plus CGD will add. So this way you can calculate both the poles, X and Y. So this is how it is plotted. So YPX is this much, PY is this much. So you can see this, X is at 5 gigahertz, but Y1 is at 400 megahertz only. So the bandwidth, these are the values which are given for this circuit. So the values are decided by the Y only, because Y is low. Okay, so the Y is low, the gain starts falling at 442 megahertz only. Like here, this is the point, 442. Till 442 the gain is same, but the gain gain starts falling at first pole, 442. So why this Y is more? So if you want to increase the bandwidth, how you can do? If you want to increase the bandwidth, what you will do? So because X is okay, X is very in gigahertz only, but you have to increase this. So Y, now how you can increase Y? You have to increase Y. How you can do that? You have to increase Y. This whole term you have to increase. This means you have to reduce C. Can you reduce C? You cannot. Okay, you cannot reduce C. Is a capacitor, it is not in your hand. But sizing of the transistor matters, because here CGD and CDB are coming. Okay, we will see either you reduce C or you reduce L, reduce load. But if load is certain given, that is a spec, he wants that I want this 5K load, I cannot reduce. So you cannot do, right? So you can see if whether you can do, try to reduce CY. Okay. So how you can reduce a capacitance? You can increase a capacitance. If one capacitance is there, you put one capacitance in parallel. With that, capacitance will increase. Increasing a capacitance is okay, but reducing a capacitance is, how you can do that? You cannot. You have to put a capacitance in series. That you cannot do. Okay. So only CDB and CGD. How now? Let us go to that CDB and CGD. CDB and CGD, gate to drain, this is overlap, and CDB, drain to base, this one. So this CGD you will not do anything, it will be fixed. CDB, it depends on the W, because I told you this capacitance will depend on the parameter of this. If W is more, because it's a cross section only, right? So this is a bottom plate. So this dimension, if they say this dimension is L1, then in this, inside the screen, that is W, right? So L into W. So it is proportional to W. Okay, so you have to reduce the width of the transistor. But that you have to see. But if you reduce W, your GM may fall. Okay, so that you have to see whether you are able to do or not. Okay, so this configuration definitely to some extent it gives a maximum bandwidth, and beyond that you are unable to do anything about this. So this it will be like that only. So now what we do is let us move further. Then we have given a here, as I told you, various stages, they are interconnected for achieving a better functionality. So this block now we have seen, this is a current buffer. What it does, if you have a lousy current source, it will make it a ideal current source. By using this stage, you are able to make a good current source, ideal current source. If in a lab you have a very bad current source, you connect that current source in with that, you may take a one transistor, bias that transistor, and connect that current source in the source to the source terminal shown like this. It becomes a better current source from the output side. Now I can put a load also here. This earlier I was putting RD. You have seen that earlier here some load was there, RD or RL. So now because here I am putting RD, so, right? What is the reason for that? You see here this RL will be, RD will also come, this RD parallel RL will come. So this RL means there is some load which is being derived, and RD is because of biasing. So total load will be RD parallel RL. It will become less. That is okay. So here if I have to increase, I am putting a diode connected load here. So let us see what are the advantages of putting a diode connected. So this transistor, now gate and source are connected, they are shorted to each other. So it becomes a diode, right? If gate and gate and drain are shorted to each other, then this transistor is always in saturation, right? It is always, this one, it is always under saturation. Gate and drain, they are shorted. This transistor is always under saturation. So what happens is, this is acting as a current source only. This is, some current is flowing, and this is acting as a current source only. So now this is X terminal, this is Y terminal. X is not changing. This is same only, right? This is not changing. These are the same, but Y will change here. Y will change. So now you see let us see at Y what are the capacitances. Now this is 1, this is 2. So what are the capacitances of M1? Those will come, CDB1 and CGD1. Earlier they were there, right? In the earlier thing, this one, CDB and CGD. These will be there. Okay, so it is there. So now, but here because of M2 also you are getting certain capacitances. So what are those capacitances which you are getting? This is drain, right? So one will be drain to body. This is drain terminal. So CD will be GS2. Why this is coming? GS2. This is gate. This is source. This is CGS here, right? This is gate. This is source. So CGS is here. So but why it is coming here? Because this gate is connected like this, right? Gate is connected to ground. So this gate to source, then this is drain to body, gate to source will come. So all these capacitances will come. Okay, so and what are the impedances here? Impedances, seeing here and seeing here, two impedances will come. At this node, if you see this transistor, what is the impedance of this transistor? 1 by GM, 1 by GM2, GM of this, it is 1 by GM2. And seeing in this here, what is the input impedance of this? This is very high, right? It will be GM into R0 into RS, but those are in parallel. 1 by GM2 is very low. A low impedance with a very high impedance is what? a very low impedance. 1 ohm with 100 ohm, if you do parallel, it will be 1 ohm only. So 100 ohm we can forget. So that is why only GM2 is written. Okay, so this is by seeing also you are able to see these results. But if these results are not clear, then you again make the model of these two transistors, write the nodal equation at this point and this point, you will get the same result. And simple arithmetic linear equations only will be there. It will get the same result. Now let us see another stage. So here you are able to little bit frequency response, you are able to adjust, you are able to change the frequency response in this. So now I wanted Y to be very high. So if because GM2 will come here, denominator. Okay, so it will be GM2 divided by this. These capacitances are almost fixed. I want it to be low, but you can adjust the GM2. You can increase pole by making GM2 very high. You got my point. So in this, because this now this transistor is not an amplifier. This is an amplifier. What if I use this only as an amplifier? It is a very good amplifier, current amplifier, but what is happening is it is giving me very good output impedance, very high, but frequency response it is 440 megahertz. I want 600 megahertz. So what I do is I replace with this transistor, which is a current source only, and I can adjust the GM2 to obtain 600 megahertz. True. Adjust means what I will adjust? W and L of this transistor. I will adjust the W because this point voltage is not in your, you cannot adjust. This is V0 here. Here you cannot do anything. So what you can adjust is you can adjust W and L to make it a very high. Okay, to make it a very high GM2 you can adjust, and here there will be some range of voltages which you can take at V0 here. So in that the current will come here, the same current I0 will come. So then only it will. Okay. I will finish in 5 minutes. 5 minutes. Okay. Queries here, right, Krish. So this is how you have seen that from a simple one stage we have added another stage. So how this, so these stages keep on adding. Another this is, I think this is not, you may not have studied in the class because normally a common gate is may not be taught, but this is a common drain which is again it you may have studied or not, but this is a basically a voltage buffer here. What is happening is the drain is common, so this point, this terminal is common. So what I do is if I connect a voltage here, this is first V bias. Okay, this is not a signal, this is a biasing because I have to make I have to bias this transistor. So this I supply and this V bias is for just for biasing only. Transistor is biased and I have to bias the transistor in saturation regions. It is biased in saturation. Now if I put a signal voltage here Vs, what will come here? The same voltage will come here. Right, at this point, source V out, same voltage will come at Vs. Okay, this is a AC voltage. If I put Vs here, the same voltage will come here V0. So that is why it's known as a voltage buffer. Then how you if you want to see why it's coming, again you draw the simple model of this and see what V0 is coming. Right, and if there is a load RL, if same voltage means approximately, actually it will come as GMRL over 1 plus GMRL. This is RL, load is connected. Actually here the gain will be V0 GMRL divided by 1 plus GMRL. Okay, so but actual result is GMRL divided by 1 plus GMRL. Right, but if GMRL is much greater than 1, GMRL is much greater than 1, then this 1 plus GMRL is GMRL only and divided by this is 1 only. It is 1 only. Okay, so I am assuming this. It is 1 only. So here Vs is equal to V0 only. So the same way, if this is already it has been done, you can see this, and this is how here GMV also will be there, and if you see the whole thing, voltage is equivalent to GM over GM plus 1, and if there is a GMB also, then it will be here GMRL plus GMBRL. GMBRL will also be there. It will keep on adding GMBRL. So these things, if you do yourself, then you can see this whole thing, and then by seeing the circuit, you can imagine what it will come. You are able to do this. Okay, so now just output. What will be the output resistance? Output resistance is very less. You can see, if you can calculate this, it is very less, because GM plus GMB. You ignore GM. 1 over GM is the output impedance, and if you GM, you make it very high, so output impedance will be very less. So here, this is what the point is. I have a voltage source, but the impedance of a voltage source should be very ideally 0. It should be very less. Okay, but it has some voltage source. It has some impedance. So how I can make a ideal voltage source? By using a voltage buffer. This is what the voltage buffer means. Okay. So you have understood these, you know about these voltage buffer, current buffer. Now, this is a voltage source, 5 volts say, and if I connect to this 1K, 5 volt will come here. But if there is some source RS, that also is 5K, so then here only 2.5 volt will come. Right, some voltage will be dropped, but I want this voltage to be very, I don't want any drop here across this. So what I can do is, I can use this with a voltage buffer, and then I can connect RL here. This is the voltage buffer. Its gain is 1. This means whatever voltage here, it's multiplied. Okay, so but here the gain should be 1 by GM, input side, and here the input impedance should be very high. Right? Now if the input impedance is very high, what happens is, this 5 volt is divided between this, and this is RS, and this input impedance, which is RN, and this voltage is fed in. If this is very high, then this whole voltage will come here. Understood or not? If this is very high, because this voltage is drop across this and drop across this only. If this is very high, if this is infinite, so at this point it will be 5 volt only, and this is 1, here it will be 5 volt, and you are connecting RN, and you see this side, it is very low, 1 by GM. Okay, so, and this voltage is this circuit which we are seeing here. We are connecting a VS here, then we are taking voltage from here, and this is for biasing here. So we are, this circuit we are putting in this. So this is how we have covered today in brief. Though actually, if correctly, if you have to do all this step by step and take some 3-4 hours to explain all these steps. Then only you can see all these calculation. But you can try at your end, because these are the most common voltage buffer, current buffer. Every analog circuit, these things will be used, and how they are used, you can see this. And by calculating various voltages, gains, input impedances, output impedances, etc. So now we will come to an end. Now if there are any questions, you please ask. We will some 10 minutes are reserved for these questions. If there are any questions, please ask.
Hello, sir. Myself Vimal Kumar Mishra from Madan Mohan Malviya University of Technology. So my question is that your slide is on the CMOS analog design, but the whole slide is covered on the analog MOS design. My question is that, hello.
Yeah.
Sir, I want to ask. So what is the analog CMOS analog design?
You see this circuit? This is NMOS. This is you see is CMOS analog design. CMOS analog design means any analog design using N transistors or P transistors. So you can see here in any analog design, sometimes we use N, sometimes we use P. You can see both the transistors are used here, right?
Okay. And
so it is not an though here if I want to use an NMOS, I can use NMOS, but I will not get the benefit.
But sir, in this circuit, you are connected with the gate terminal to the with the source terminal.
It's a gate drain connected.
Yes, sir. This is not for complete NMOS design, sir.
This is.
Sir, in this circuit, you are connected a gate terminal to the source terminal. In my opinion, this is not for the.
This is gate to drain. This is drain.
Yes, sir, gate to drain. And I think this is a behave like a diode, not a behave like a NMOS. So sir,
no, this is already it's already written. It's a diode connected load. Diode connected load means it's basically it is a current source.
Yes,
sir. In the beginning only, I told you that transistors are used as resistor, capacitors, current sources, other things. So in this, you see, if a transistor here, this transistor will always be under saturation. Why? Because under saturation there are two conditions. One, your VGS should be greater than VT and VDS should be greater than VGS minus VT. Okay. So it will meet those two conditions. Because your gate and drain are shorted. So VDS will always be greater than VGS. Because your drain voltage and gate voltage is same. True. So whenever you are using this MOS, it is a transistor only, it's a MOS transistor, but it is getting operated in those curves. That is why I told this is important to understand those curves. So in those curves like this, so it is in this region only, where it is behaving as a current source only. Okay, but why it is useful? Because it is useful, we are able to control. Our aim is, actual circuit is this only, which is a current buffer, but we want to increase the bandwidth. Okay, if I put an RD here, because this stage has to be biased. You understand my point? This M1 has to be biased. How can I bias? By putting an RD. So I will put a VDD RD here. Okay, but then RD is reducing here. It is reducing the pole. So I have to increase the pole. So I am eliminating RD and I am putting a diode connected load here. And by adjusting the GM of this, I am able to increase the band. This is the reason. And another reason is, if I put an RD resistor in a IC are very expensive. I will cover in the next lecture how resistors are made, and they occupy lot of area. They occupy lot of chip area. One resistor may occupy area of say 100 or 1000 transistors. Okay, so if I put a transistor here, I am able to make it a very small, this circuit within a very small area. That is much easy for me. So resistors are avoided. Another reason, the variation in the value of resistor in a chip can be 20%. So if you have a resistor of 1K, it can vary by 20%, its absolute value. So that are also another reason why they are avoided. So normally resistors are avoided. That is why you will find in any CMOS design, you will find these kind of. Now here you tell me whether you can, if you use an NMOS, what will happen? You try. You can use an NMOS also. What it will be? This will be source, right? So here gate cannot be connected to like this. So gate, you have to give a bias voltage at gate, right? So you have to connect. You have to give a VB here, and you have to give such VB such that this transistor is always in saturation. So, but only thing is you have to generate VB now. If that VB is say 500 volt, 500 millivolt, so you have to generate 500 millivolt here. That is the reason. But here I don't have to generate any voltage. I have just connected here to make this under. So this is easy for. It is not that you, and this also you can have a PMOS also. So all these variations are there. It depending on your situation, you can choose any of these. Any next question?
So next question is invited.
So from ABS, we have one question, please. Can you hear me?
Yeah, you please carry on.
Hello, sir. Myself, Arti from ABS Engineering College. I have a question. What will be the effect of Birdsbeak phenomena on the VI characteristic of the MOSFET? And another thing is, do we include the Birdsbeak phenomena while modeling the MOSFET?
Which phenomena?
Birdsbeak phenomena.
Bird beak.
Yes.
Bird beak? No. This actually, this your that is a locus. When we were using local oxidation, that time bird beak was coming. That it does not have any effect on the MOSFET characteristics. What effect it has? It increases the area. That is how. But that till 1 micron technology, that bird beak was happening because we were using locus, local oxidation. But now we are using a shallow trench isolation. I will explain, but it bird beak has nothing to do with the MOSFET characteristics.
Thank you, sir. Another question?
You see, first let me explain. If you want to know exactly what happens is, this is the thing here. Look, so this is the. So your transistor is coming here. This is the well. Transistor is sitting here, and this is known as a bird beak here. So the thing is, here this length is around 40% of the it is occupying 40% of the area. This is the isolation area. So this is the beak, which is occupying 40% of the isolation area. So my one transistor is okay. So in the new technology, we are using shallow trench isolation. Shallow trench isolation means you are making here trenches like this and filling with high electric HDP. You fill like this, right? So you're making the circuit area less, and you are able to make the circuit denser. But it has no effect on the MOSFET characteristics. So it is not a part of MOSFET. It is a part of the isolation module which separates two transistors.
Hello. So, Nitin from VLSI Engineering College. I have one question. How do we say that MOSFET behaves like an inductor? And can we have some application of MOSFET as an inductor? Can you elaborate that? Thank you so much.
Yeah, single MOSFET does not behave. Single MOSFET does not behave like an inductor. But we can make a circuit using op-amp, which will give, by which you can analyze an op-amp that is known as an active inductor. Right. So by using an op-amp, we can realize inductor, which is known as inductor, and they are commonly used in analog design. You see this, it's very difficult to otherwise make inductors. And you can, there are two types of inductor, passive inductor and active inductor. Active inductor you can realize by using op-amp, and op-amp is made by using MOSFET. And passive inductor means, again, this metal coils you have to use. So these metal things you have to use, but the problem is that the resistance potential is very less.
Thank you, sir.
I have a question. Why we are using diode in this configuration, in this EG configuration?
No, this diode is, you see, here, the reason I told you, if I put a resistor here, right? So this at RD, if I put the which is coming because of resistor is at a low frequency. So this whole this configuration is not able to, I am not able to get the bandwidth. I showed some value, some 440 megahertz was coming. So I have to increase the, so what I can do to increase, because R is coming in the denominator side. If you see, the R is coming here, denominator. If I go to that, you can see where R is coming, and that it's difficult to manage with. This RL is there, right? This it is coming here. So this RL means it is some load here and some RD. Now the value of RD is fixed. How? Because this VDS, you have to make a VDS which is greater than VGS minus VT. There will be, you have put a VB here, you have put some VG. So this VD, how you will calculate RD? You have to decide what VDS you want. So based on this, value of RD will come, which will be a high value, and this high value means the pole at Y is coming lower. So this, you can see this pole is coming at 442 megahertz. So I want to shift this to a higher bandwidth. Then what I have to do? I have to increase this. I have to decrease this R. So I cannot decrease this R. I have to change this, because if I decrease this R, if I decrease, I cannot change this value, because this value is dependent on VDS, right? If, or in other way, if you see, if you decrease this, what happens? Voltage drop here across R will be more, because you assume some constant current is flowing like this, like this. So if I decrease this value of R, so the voltage drop across here will be less, and more voltage is dropping here. So VDS is increasing. So then you have to increase VGS also, VG. This also you have to increase. So this voltage and VD and VG, they are correlated with each other. So this RD, you cannot play with the RD. This RD will be fixed, and I want to eliminate this RD. The best thing is I will use this as a current source. So what this configuration for a simple thing is like this. So there are two, one is R and another is this one. You see, if some current is flowing here, there will be some drop across this. So here this is say 3 volt, so it eats up some voltages, right? And here now there is some current source here. This value is fixed, because this value VD is correlate with VGS, because your VDS should be greater than VGS minus VT. So based on that, the value of R will come in a design. Okay, so this R will decide the pole of here. The pole will come at a low thing. Okay, I am unable to reduce the value of R. So what I will do is, I will remove this. I will put a diode connected this thing load here. So it's basically a current source. So here value of this can be adjusted here. In this, across this, the value can be adjusted here, which is not possible by using an R. So that is the reason of putting this diode connected load. You see, everywhere you will not find a resistor. In very few places only you will find resistors. In analog design, most of the time we will try to make this active load. This is known as an active load. So diode connected load. So there are some added advantages. It takes less area. Moreover, there is no power dissipation. There are many reasons for this. Okay, next question.
Hello. Hello, sir. Myself from MMUT Gorakhpur. My question is, can we use CMOS for high frequency like microwave range?
CMOS are used nowadays. CMOS, you can design circuits till 20 gigahertz, 25 gigahertz. You can use CMOS. Sir, and people are using CMOS for till 15-20 gigahertz. This low 45 nanometer, 25 nanometer devices are being used. But if you want to go beyond 20, then you have to go for HBT or gallium arsenide.
Sir, but if you are going for high frequency, then should we consider parasitic inductive effect?
Yes, yes, it will come. Definitely, it will come.
Hello.
Hello, it will come. Parasitics will come always. It will affect your high frequency response.
But sir, how it can be calculated? Any source? Can you say, sir?
No, the parasitic in the sense, you see, this is what the scaling is. You are reducing the size of the transistor, right? Once you are reducing the size of the transistor, its bandwidth increases. You are reducing L, you are reducing W, the bandwidth increases. So that is why I am telling you this. You cannot use big size transistors, more than 2 gigahertz or 1 gigahertz. Only small size, which like 25 nanometer, 45 nanometer transistors. Pentium chip, which Intel, I think they are working till 3 or 4 gigahertz, they are at 45 nanometer. And you can increase to some 8 or 10 gigahertz, but if you want to go beyond, then you have to change silicon. All these transistors, CMOS is based on silicon, and you have to go to gallium arsenide or GaN, gallium nitride. So there, because mobility is restricted, their mobility is more in gallium arsenide. So there you will get a better response, high frequency response. And moreover, this whatever you are mentioning high frequency, that is only for military application. There gallium arsenide is used. Normally in a commercial use, it is not required.
Sir, can you tell me some book or some any link related to this inductive effect for high frequency for CMOS?
High frequency CMOS, you go to this IBM website, you will find IBM high frequency CMOS circuits. You will find lot of literature. IBM, or you go to Intel website. Many articles, many information is available on the net.
Okay, sir. My one more question is that most of the time, or I have seen all the time when we design MOSFET, we consider length and width of channel. Don't consider length and depth of the source and drain. Then, sir, how we can decide? Is there any effect of that?
Common gate configuration.
Yeah. Can you repeat the question?
Sir, my question is this: when we design MOSFET, we consider
just wait. Just wait.
Pardon, sir?
Please ask question one by one. Two people are talking together, so we are getting two voices.
Okay, sir. I'm asking a question related to when we design MOSFET, we consider length and depth of the channel, but we don't discuss about length and depth of the source or drain. Sir,
that is not in your hand. That is not in your hand. You cannot change source and drain. You see, that is a technology parameter. You can change only L and W. That is the width of that XJ, that source and drain. That is not in your hand. It's a technology. It's fixed for all transistors. It is not changed.
Sir, if you change any, there will be any effect?
No, it will not affect. It will not affect. It is changed. You see, when you design a circuit, now the technology kit is given, technology file is given. Certain things you can change, certain things you cannot. That is fixed. That is a part of technology. So your dimensions of drain and source, how the depth of implant, the XJ, the width of implant you can change, but not the depth. That you cannot change. So and moreover, it has no effect. It has effect on CGS, CDB are given. CGS, CDB you cannot change.
So I think we can have one more query, and now JEC, REC can ask their question. Then we will have lunch break because we are already running short of time. And maybe after lunch break we can have we have one more session. After that we can have more queries. So we can have question from JEC, RC. Yes.
So generally, which kind of MOS transistor is used for getting more amplification current by common gate configuration?
Both, no issue at all. You can use both. You can use it. You can use N. You can use P. It depends in a bigger circuit, like which one matches your. You see here, if you see, because it depends on your convenience. Here a voltage range will come here. It is not that you can get any voltage. There is here some voltage range will come, and if this node is getting connected to some other circuit, it is driving some other node. Then you have to see like the compatibility, the voltage range of that stage, how it is compatible, and based on that you will decide whether it's going to be a P or an N. It is like that only. So otherwise both can be used. They are complementary. That is why the word complementary is there. So they can complement for each other. It is not that here. Only thing is, if you have to take a current, like then you will use a P. If you have to source a current, if you have to sink a current, you will go for a NMOS. If you have to source, then you can go for a PMOS. You can see here, this is the PMOS. So in the current is coming from here, the current comes in this direction. You see, this is source, this is drain. So for a PMOS, the current is coming out of drain. Okay, so it's a source. But for an NMOS, what is happening? It is sinking. The current is going inside the drain. Here, the current is going inside the drain. So this key, you should keep this in mind, and depending on the situation, anything can be used.
So I think now it is clear to you. Now we can have a break for lunch, and we will be back at sharp 2:30. And before that, I have one just information for all the local coordinators. At present, 24 centers are connected. So all of you local coordinator of all the centers are requested to kindly send me one acknowledgement mail. Means you are connected today, and also give me the information about total number of participants at your center. So send me this mail by today itself. So we can have a break for an hour, and we will be here at 2:30, and we will continue with our session of Engineer HS Jatana from SCL Mohali. So enjoy your lunch. Thank you. Thank you very much.
We will be having one intermediate, and today constraint we can go down, and at the end of the next session we will turn things to analyzing the and innovative answers we have right. Now
अच्छा वो तुम्हें क्या काम है इनको देते हैं वो राकेश तुम ना ऐसा करना जितने भी स्पीकर आएंगे सबका पीपीटी जो है ऊपर एक फोल्डर बना लेना VLSI डिजाइन करते हैं इसमें उसमें सेव करना सारी पीपीटी ठीक है एंड में भेज दीजिए सेंटर्स में ठीक है ये पीपीटी वाला काम सारा तुम्हारा रहेगा सारी पीपीटी तुमने प्रोवाइड कर दी ठीक है ये डीएम वाला तुम रामपाल जी के साथ करोगे ठीक है और मैंने ठीक कर दी तो हम लोग भी लंच कर लो ठीक है तो लंच के बाद में फिर लंच क्या है अरे हम फिर 2:30 बजे मिलते हैं ठीक है लंच कर लो तो बाकी क्या होगा ये सब होगा तो आईडी करके
ये हम देख रहे हर सेंटर का तो ये रहा
उनका 81 है ना 81
ये हमने अभी वो सेट कर देंगे हमको पूरा होल्ड हो गया तो कहीं और भी लगेगा ना खाली आप तेरे उस पे डाल
डेढ़ साल और लगी हुई है तुमको एक सर्वर लगनी चाहिए
ये ठीक है अब हम चाहे तो ये